We think we are smart. We have smartphones and satellites. We can edit genes and print 3D organs. We look back at the past and see simple people living simple lives. But what if we are wrong? What if the past was not so simple? What if ancient people knew things we have only just rediscovered? Imagine finding a clockwork computer in a 2,000-year-old shipwreck, or a battery from ancient Iraq, or a recipe for concrete that is better than our own. These things are not science fiction. They are real. They were found. They sit in museums, challenging our ideas about history. They show us that ancient inventors were not just chipping away at stones. They were creating things that were, in some cases, thousands of years ahead of their time. How did they do it? Where did this knowledge come from? And, more importantly, what else have we lost? Number 19, could the Romans see nanoparticles? There is a cup in the British Museum. It is called the Lycurgus cup, and it looks like a normal, dull, green glass cup. Nothing special. But if you shine a light from behind it, something incredible happens. The cup glows a deep, vibrant red. It is a trick of the light, a piece of ancient magic. Except it is not magic. It is nanotechnology. The cup was made in the 4th century AD by Roman glassmakers. For centuries, nobody knew how it worked. It was just a beautiful, strange object. Then, in 1990, researchers in England took a tiny fragment of the glass and put it under a powerful microscope. What they found was shocking. The glass was filled with microscopic particles of gold and silver. These particles were incredibly small, about 50 nanometers in diameter. That is 1,000th the size of a grain of salt. This is what scientists today call dichroic glass. The way the light reflects or passes through these tiny metal particles determines the color you see. When light hits the cup from the front, the metal particles reflect a greenish-yellow light. But when light passes through the glass from behind, the particles scatter the light in a way that makes it look red. The effect is precise. It depends on the exact size and density of the nanoparticles. If the particles were too big or too small, it would not work. This is a level of material science we have only mastered in the last few decades. We use nanoparticles today in medical diagnostics, electronics, and stain-resistant clothes. The Romans were doing it 1,600 years ago. The people who made this cup achieved a level of control over matter that should have been impossible. They did not have electron microscopes. They did not have our understanding of physics or chemistry. So how did they do it? The most likely answer is that it was a happy accident. They probably ground gold and silver into a fine dust and mixed it into molten glass. They must have learned through trial and error that a tiny amount of this metal dust created this incredible effect. They were following a recipe, not a scientific formula, but what a recipe. To create something so precise by accident seems almost impossible. The cup depicts a scene from the myth of King Lycurgus, which suggests it was a luxury item, not a failed experiment. It was made to be admired. The Lycurgus cup forces us to ask some uncomfortable questions. It shows that ancient craftsmen could produce materials with properties we have only recently understood. It was not a fluke. Other Roman glass fragments have been found with similar properties. This was a known, if rare, technology. A technology that was then lost for over a millennium and a half. Did the Romans understand what they were doing on a chemical level, even in a basic way? Or were they just incredibly skilled artisans who perfected a technique without knowing the science behind it? How many other ancient artifacts that we see as just art are actually examples of a lost science we do not recognize? And if they could do this, what other secrets were dissolved in the molten glass of their furnaces? Number 18, how did a sword cut silk in midair? Legends from the time of the Crusades tell of remarkable swords. The European knights wielded heavy broadswords designed for crushing blows. Their Saracen opponents, however, had something different. They had curved sabers that were said to be so sharp they could cut a silk scarf falling through the air. They were so strong they could cleave through a knight's iron helmet without losing their edge. These were not just swords, they were Damascus steel. For centuries, the secret of how to make this steel was one of the most guarded mysteries in the world of metallurgy. The blades were easily recognized by a unique, beautiful pattern on their surface, like flowing water. This pattern was called damask, and it was a sign of the blade's incredible quality. Then, around the year 1800, the knowledge was lost. The swords could no longer be made. The recipe vanished. For 200 years, modern scientists tried to figure it out. They analyzed the blades, they tried to reverse engineer the process, but they could not replicate the combination of flexibility, strength, and a perpetually sharp edge. The secret seemed lost forever, until the 1980s and 90s, when modern science finally caught up with ancient craftsmanship. Using scanning electron microscopes, researchers, including Dr. J.D. Verhoeven of Iowa State University and metallurgist Alfred Pendray, discovered the secret. The steel was full of carbon nanotubes. These are microscopic cylindrical structures made of carbon atoms. They are among the strongest materials known to science. We only discovered them in 1991. Yet, here they were in swords forged over 1,000 years earlier. The process started with a special kind of raw material called wootz steel. It was made in India and Sri Lanka and exported to the Middle East. This wootz cake contains specific trace impurities like vanadium and molybdenum. These impurities acted as catalysts. Blacksmiths in Damascus and Persia would then forge the wootz steel at a very specific, relatively low temperature. This careful process of heating and hammering caused the carbon atoms in the steel to align and form these incredibly strong nanotubes and nanowires. The watery pattern on the blade was the visible sign of these microscopic structures. The knowledge was not lost because the blacksmiths forgot the technique. It was lost because the raw materials ran out. The specific mines in India that produced wootz steel with the right chemical cocktail were exhausted. When blacksmiths tried the same recipe with different steel, it did not work. The magic was in the ingredients as much as the method. This was not just good blacksmithing. This was a form of nanotechnology achieved centuries before the word or the concept even existed. The smiths who made these blades were manipulating matter at a near atomic level without even knowing it. They were working with a level of materials science that we have only recently begun to understand. They were not just making a tool, they were engineering a super material. So how did ancient smiths, through trial and error, develop a process that created materials we only recently discovered with our most advanced instruments? What other lost technologies are not based on a forgotten technique, but on a raw material that no longer exists? And does this mean that ancient people had a deeper, more intuitive understanding of materials than we give them credit for? Number 17, was there a computer in ancient Greece? In the year 1900, a group of sponge divers were working off the coast of the Greek island of Antikythera. They were seeking shelter from a storm when they found a Roman shipwreck. The wreck was full of statues and pottery. It was a major archaeological find, but hidden among the treasures was something else. It was a lump of corroded bronze, about the size of a shoebox. It looked like a rock. For decades, it sat in the National Archaeological Museum in Athens, largely ignored. Then, in the 1950s, a historian named Derek DeSola Price began to study it. He realized it was not a rock or a broken statue, it was a machine. A machine with intricate gears and dials. Using the 10th rays in the 1970s, and later more advanced CT scanning in the 2000s, were able to see inside the corroded lump. What they saw was breathtaking. Inside was a complex system of at least 30 interlocking bronze gears. The complexity was unlike anything seen from the ancient world. This was the Antikythera mechanism. Research by the Antikythera Mechanism Research Project, a team of international experts, has revealed its purpose. It was an analog computer. It was designed to predict the positions of the sun, the moon, and the 5 planets known at the time. It could predict eclipses. It had a dial that tracked the 4-year cycle of the Olympic Games. The mechanism was built around the 2nd century BC. To put that in perspective, the next time we see technology of this complexity with gears this intricate is in the astronomical clocks of 14th century Europe. That is a gap of over 1,500 years. The Antikythera mechanism is a complete anomaly. It is like finding a jet engine in a medieval castle. The front of the device showed the positions of the celestial bodies in the zodiac. The back had dials that showed lunar cycles like the Metonic cycle, a 19-year pattern. The gears were incredibly sophisticated. It even used a differential gear, a device that allows for the addition and subtraction of angular velocities. This was a concept that was thought to have been invented in the 16th century. The Greeks were using it to model the irregular orbit of the moon. The existence of this device changes everything we thought we knew about Greek technology. We knew there were brilliant philosophers and mathematicians. We knew about Euclid and Pythagoras. but we thought their engineering was limited to simple machines like levers and pulleys. The Antikythera mechanism shows they could translate their advanced astronomical theories into a working physical model. This was not just theory. This was applied science of the highest order. The device was probably built on the island of Rhodes, which was a center for astronomy and engineering. The great astronomer Hipparchus, who worked there, is a likely candidate for its designer. But the questions it raises are profound. Was this a one-of-a-kind device, the work of a single forgotten genius? Or were there many of these machines? Cicero, a Roman writer, mentions two similar devices, but his descriptions were always thought to be exaggerated. Now we know they were probably real. If they could build this, what else could they build? Did they have other complex machines that have been lost to time? Their bronze gears melted down long ago. And how could all of this knowledge, this incredible expertise in mechanics and gear cutting, just disappear from the world for 15 centuries? Number 16, did they have batteries in the Baghdad Museum? In 1938, Wilhelm Koenig, the German director of the National Museum of Iraq, was sorting through artifacts. He came across a small, unassuming object. It was a clay pot, about 6 inches tall. Inside the pot was a copper cylinder, and inside the copper cylinder was an iron rod held in place by an asphalt stopper. It did not look like much. It was cataloged as a ritual object, but Koenig had a different idea. A radical idea. He thought it looked like an electric battery. The object, now known as the Baghdad Battery, dates from the Parthian or Sasanian period, sometime between 250 BC and 250 AD. On the surface, the design is simple. You have two different metals, the copper and the iron. All you need is an electrolyte, an acidic liquid like vinegar or grape juice, to create an electrical charge. If you fill the pot with vinegar, a small voltage is produced between the copper and the iron. It works. Replicas of the Baghdad battery have been made, and they produce a current of about half a volt. This discovery was, and still is, highly controversial. The mainstream view among archaeologists is that these were not batteries. They were likely storage vessels for sacred scrolls. The scrolls, made of papyrus or parchment, would have decomposed, leaving only the metal components behind. This is a plausible explanation, but it does not explain everything. Why use copper and iron? Why the specific design? If they were batteries, what were they used for? Half a volt is not much power. You could not light a lamp with it, but you could do other things. One theory is that they were used for electroplating. By connecting several batteries together, you could generate enough current to apply a thin layer of gold or silver onto another object. This was a known practice in the region, but it was thought to be done with other methods. Another idea proposed by Paul Craddock, a metallurgist at the British Museum, is that they were used for a kind of mild electrotherapy. The ancient Greeks knew about static electricity and the electric shock from certain fish. It is possible that priests or healers used the gentle tingle from these devices to create a sense of mystery or to treat minor pains. It would have felt like magic to an unsuspecting person. We have no written records from that time that mention these devices or their use. There are no diagrams, no instructions. All we have is this collection of strange clay pots. Many were found, not just one. This suggests it was a known technology, not a one-off curiosity. The debate continues to rage. Were they just scroll jars? Or did an ancient civilization, 2,000 years before Alessandro Volta invented the first modern battery in 1800, stumble upon the secret of electricity? If they were batteries, why is there no other evidence of a knowledge of electricity? Where are the wires? Where are the electroplated objects that can be definitively linked to this method? Could a civilization discover a fundamental force of nature like electricity and then use it for nothing more than cheap jewelry or magic tricks? Or is it possible that its true purpose was something we have not even imagined yet? Number 15, why is this 3,000-year-old pillar still not roosting? In Delhi, India, there is a pillar of iron. It stands in the Kutubi complex. It is over 23 feet tall and weighs more than 6 tons. What is remarkable about this pillar is not its size, but its age and condition. It was erected in about 400 AD. That means it has been standing exposed to the wind and rain for over 1,600 years, and yet it has barely rusted. Any modern iron structure of that age would have corroded into a pile of dust long ago. But the iron pillar of Delhi stands almost pristine. For centuries, its resistance to rust was a mystery. It was seen as a testament to the lost skills of ancient Indian blacksmiths. It was so unusual that some even suggested it was made from a meteorite or by aliens. The truth, as modern science discovered, is just as impressive. In the 1960s, and with more detail in the early 2000s, metallurgists from the Indian Institute of Technology Kanpur, led by Dr. R. Balasubramaniam, finally solved the puzzle. The answer lies in the unique way the pillar was made. It was not cast from molten iron in a single piece. That would have been impossible with the technology of the time. Instead, it was made by hammer welding small lumps of iron, one by one. This process is called forge welding. The ancient smiths used charcoal to heat the iron ore. This method did not get hot enough to melt the iron completely, so it created lumps of iron with a lot of impurities trapped inside. One of these impurities was phosphorus. In modern steelmaking, phosphorus is considered a bad thing. It can make steel brittle, but in the case of the Delhi pillar, it was the secret ingredient. Over the centuries, this high phosphorus content in the iron reacted with the oxygen and moisture in the air. This reaction created a very thin protective layer on the surface of the pillar. This layer is a compound called a passive protective film, made of iron hydrogen phosphate hydrate. It is only a few micrometers thick, thinner than a human hair, but it is incredibly dense and stable. It seals the iron from the elements, preventing the electrochemical reactions that cause rust. Essentially, the pillar created its own rust-proof coating. It was an unintentional but brilliant piece of chemical engineering. The ancient Indian metallurgists did not know about phosphorus or passive protective films, but through generations of experience, they had perfected a process that produced an incredibly durable, weather-resistant iron. They were masters of their craft, achieving results that modern science struggled to explain for decades. This was not a one-off. There are other large ancient iron objects in India, like the iron beams at the Konark Sun Temple, that show similar resistance to corrosion. It was a known technology, a technology that was incredibly advanced for its time and in some ways superior to our own methods for preventing rust. How did these ancient craftsmen perfect a process whose chemical basis they could not have understood? Was the high phosphorus content a deliberate choice or a lucky property of the local iron ore they were using? And if we lost this simple effective method for creating rust-proof iron, what other subtle but powerful material sciences have we forgotten? For number 14, could a Greek toy have started the Industrial Revolution? In the 1st century AD, a brilliant inventor lived in the city of Alexandria, Egypt. His name was Hero, or Heron. He was a mathematician and an engineer who wrote extensively about mechanics, pneumatics, and automation. He invented a coin-operated holy water dispenser, a water pump, and even automatic doors for a temple. But his most famous invention was a simple, almost toy-like device called the aeolipile. The aeolipile was a hollow sphere mounted on 2 pipes so that it could spin. The pipes also fed steam into the sphere from a cauldron of boiling water below. The sphere had 2 bent nozzles pointing in opposite directions. When the water boiled, steam would rush into the sphere and shoot out of the nozzles. This jet of steam would push the sphere, causing it to spin rapidly. It was a reaction engine. It was the world's first steam engine. Hero described it in his writings, but he treated it as a curiosity, a temple wonder to impress people. There is no evidence that he or anyone else in the ancient world saw its potential. They did not connect it to work. They did not use it to power a machine or pump water. It was just a fascinating demonstration of the power of steam, a clever toy. And then nothing. The idea of using steam power to create motion disappeared for over 1,500 years. It was not until the 17th and 18th centuries that inventors like Thomas Savery, Thomas Newcomen, and James Watt developed the steam engines that would power the Industrial Revolution. They changed the world. They built factories, powered trains, and created the modern industrial economy. Hero of Alexandria had the key in his hands in the 1st century AD. He had the fundamental principle of the steam turbine. The technology was there. The Romans had the metalworking skills to build a larger, more powerful version. So they had a need for power for things like draining mines or grinding grain, which they did with animal or human labor. So why did it not happen? This is one of the great what-ifs of history. Some historians argue that the Roman economy was based on slave labor. There was no economic incentive to develop labor-saving machines. Why build a complex engine when you could just use more slaves? Others suggest that the scientific and the practical worlds were separate. Inventors like Hero were seen as philosophers and entertainers, not practical engineers who could solve real-world problems. The idea of applying this magic to everyday work just did not occur to them. Whatever the reason, the Aeopile remained a curiosity, a brilliant idea that was born centuries before its time. It shows that sometimes having the technology is not enough. You also need the right social, economic, and cultural conditions for that technology to take root and change the world. The Greeks and Romans had a piece of the Industrial Revolution, but they left it on the shelf. What would our world look like if the Industrial Revolution had started in ancient Rome? Would they have built steam-powered chariots and factories? Could they have avoided the so-called Dark Ages? And how many other revolutionary ideas are sitting in old texts, dismissed as mere curiosities, waiting for someone to see their true potential? Number 13. How did the Romans heat their homes from the floor? Imagine a home in the cold, damp climate of Roman Britain in the 2nd century AD. Outside, it is freezing. Inside, the rooms are warm, not from a smoky open fire in the middle of the room, but from the floor itself. The tile floor is pleasantly warm to the touch. The heat rises gently, warming the entire space evenly. This was not magic, this was the hypocaust system, the Roman invention of central heating. The hypocaust, which literally means heat from below, was a brilliant piece of engineering. It was essentially a raised floor. The floor of the villa was built on top of a series of short pillars called pillae. This created a hollow space underneath the living area. Elsewhere, a large furnace was kept burning. The hot air and smoke from this furnace were channeled into the hollow space under the floor. The hot air circulated beneath the tiles, heating the floor above to a comfortable temperature. The floor acted like a giant radiator. In more luxurious buildings, the hot air was also channeled up through hollow tiles or pipes inside the walls, heating the rooms even more effectively. The smoke and fumes were then vented out through a chimney on the other side of the building. It was an ingenious system. It provided clean, smoke-free heat. It was far more efficient and comfortable than an open fire. The invention is often credited to a Roman engineer named Sergius Orata around 80 BC. It was most commonly used in public bathhouses where vast amounts of hot water and steam were needed. The floors of the hot rooms, the caldarium, could get so hot you had to wear special wooden sandals. But the system was also adapted for private villas in the colder northern provinces of the Roman Empire. This was a level of domestic comfort that would not be seen again in Europe for over 1,000 years. After the Roman Empire fell in the 5th century, the knowledge of how to build and maintain hypocaust systems was lost. Throughout the Middle Ages, people went back to huddling around open fires in the middle of drafty great halls. Central heating became a forgotten luxury of a lost civilization. It was not until the 19th century that similar systems of central heating became common again. The Romans had a sophisticated understanding of thermodynamics and fluid dynamics. They knew how to control the flow of hot air to heat large, complex buildings. They developed the specific building materials like the special tiles and cement needed to make the system work without cracking or setting the house on fire. It was a complex, integrated system of architecture and engineering. Why was such a practical and beneficial technology completely abandoned? Was it simply too expensive and complex to maintain after the collapse of the Roman economy? Did the skilled engineers who knew how to build them simply disappear? And how did people in places like Britain endure over 1,000 years of cold, damp winters, knowing that a far superior technology had once existed right beneath their feet? Number 12, did the Romans have indoor plumbing? When we think of Rome, we often think of legions, emperors, and gladiators. But perhaps their most impressive and lasting achievement was their mastery of water. The Romans were the greatest hydraulic engineers of the ancient world. They built aqueducts, massive stone channels that carried fresh water for miles from distant springs into their cities. The city of Rome itself was supplied by 11 aqueducts, delivering over 1 million cubic meters of water a day. This was more water per person than many modern cities have today, but getting the water to the city was only half the battle. The Romans also figured out how to manage it once it arrived. This water fed public fountains, elaborate bathhouses, and the homes of the wealthy. The rich had running water piped directly into their villas. They had lead pipes fistulae that brought in fresh water and drains that took away waste. They had taps or stopcocks made of bronze to turn the flow on and off. They had flushing toilets. The Roman toilet, or latrine, was often a communal affair, with long benches of stone or wood with holes cut in them. A constant stream of water flowed in a channel beneath the seats, carrying the waste away into a central sewer system. The most famous of these sewers was the Cloaca Maxima in Rome, a massive underground channel that is still in use today. It was an incredibly sophisticated system of urban sanitation. This level of public health infrastructure was unprecedented. It allowed Roman cities to grow to sizes that would have been impossible before, supporting populations of up to 1 million people. By providing clean water and removing waste, they dramatically reduced the risk of waterborne diseases that plagued most ancient cities. It was a revolution in urban living. The engineering was remarkable. They understood concepts like gravity flow and hydraulic head. They built inverted siphons to carry water across deep valleys. They used materials like waterproof concrete, developed by mixing volcanic ash pozzolana with lime. The quality of their work was so high that some Roman aqueducts, like the Aqua Virgo in Rome, are still in use, supplying water to fountains like the Trevi Fountain. After the fall of Rome, this knowledge was lost. The great aqueducts fell into disrepair. The sewer systems clogged and were forgotten. European cities became filthy, unsanitary places. Waste was thrown into the streets. People drank from polluted rivers. For over a millennium, the basic principles of hygiene that the Romans had mastered were ignored. It was not until the great public health crises of the 19th century, with outbreaks of cholera and typhoid, that cities in Europe and America began to rebuild the kind of water and sewer systems that the Romans had taken for granted. How did the Romans develop such a comprehensive and systematic approach to water management? They did not have modern pumps or power tools. It was all done with gravity, manpower, and an incredible understanding of engineering. What was it about their society that placed such a high value on public health and civic infrastructure? And how could humanity forget something as fundamental as the link between clean water, sanitation, and health for so long? Number 11. Could ancient surgeons operate on the brain? For most of history, surgery was a brutal and often fatal affair. Without anesthesia, without a knowledge of germs, operations were a last resort. But ancient people were not as ignorant as we might think, and in one particular area, they performed a procedure that is shocking in its audacity. They operated on the human brain. The procedure is called trepanation. It involves drilling, cutting, or scraping a hole into the skull of a living person. And it is one of the oldest surgical procedures known to humanity. Skulls with the telltale holes of trepanation have been found all over the world, from Europe and Asia to the Americas. The oldest examples date back to the Neolithic period, over 7,000 years ago. Why would they do this? The most common theory is that it was a way to treat head injuries. If someone suffered a blow to the head, it could cause swelling or bleeding inside the skull. This pressure on the brain could be fatal. Opening a hole in the skull would relieve that pressure. Modern neurosurgeons do a similar procedure today called a craniotomy. Evidence on the skull supports this theory. Many show signs of fractures near the trepanation hole, but there are other reasons too. It may have been used to treat conditions like epilepsy or severe headaches, which were perhaps thought to be caused by evil spirits trapped inside the head. Cutting a hole would let the spirit escape. What is most astonishing is that many people survived. We know this because the bone around the edge of the hole shows signs of healing. In some skulls, the edges are smooth and rounded, indicating that the person lived for months or even years after the operation. In some archaeological sites, particularly in ancient Peru, the survival rate appears to be as high as 70 or 80%. This is a staggering figure for prehistoric brain surgery. The surgeons used simple tools, often made of sharpened stone like obsidian. They would have needed a deep understanding of the skull's anatomy to avoid cutting the delicate membranes and blood vessels covering the brain. They likely used primitive anesthetics or sedatives, perhaps from plants like coca leaves or certain fungi. They would have also needed some knowledge of antiseptic practices to prevent infection, perhaps using herbs or tree resins known for their antibacterial properties. Your Roman physicians like Celsus and Galen wrote about the procedure. They described using specialized tools, including a circular drill called a modulus. They understood the risks and described the proper techniques. This was not butchery. In the hands of a skilled practitioner, it was a life-saving medical procedure. After the Roman era, the practice declined in Europe, often becoming associated with quackery. But the fact remains that for thousands of years, ancient and prehistoric people were successfully performing brain surgery. They were cutting into the very seat of consciousness with nothing but stone tools and incredible skill. How did prehistoric people develop such a risky and complex surgical technique? Was it through trial and error with countless failed attempts? How did they manage pain and infection with such a high success rate? And what does it say about their understanding of the body, that they knew that an injury inside the head could be treated by making an opening from the outside? Number 10, how were Roman doctors so good at surgery? When we imagine ancient medicine, we might think of potions, prayers, and superstition. But in the Roman world, there was another side to healing surgery. Roman surgeons were highly skilled professionals who could perform a surprising range of complex operations. Their success was built on two things: a deep practical knowledge of anatomy and a stunning array of specialized surgical tools. Archaeological sites like Pompeii have preserved entire sets of Roman surgical instruments. They are made of bronze, iron, or steel, and they look remarkably modern. We can see scalpels of various shapes and sizes, sharp hooks for retracting tissue, forceps for clamping blood vessels, and bone saws for amputations. They had catheters for draining fluid, speculums for examinations, and drills for brain surgery. Some of these tools are so well designed that their basic form has not changed in 2,000 years. The Roman surgeons served in the military, which gave them extensive experience in treating trauma. On the battlefield, they learned how to extract arrowheads and spear points, how to set broken bones, and how to perform amputations. They understood the importance of speed and cleanliness. While they did not have a full germ theory, writers like Galen advised that wounds should be kept clean, often with wine, which acted as a mild antiseptic. But their skills went beyond military medicine. They could perform delicate eye surgery to remove cataracts. They operated on hernias and removed bladder stones. They had tools for tonsillectomies. There is even evidence they performed a procedure similar to a cesarean section, although likely only on mothers who were already dead or dying in an attempt to save the baby. The key was their understanding of anatomy. While human dissection was not widely practiced due to social taboos, surgeons learned from treating wounds and from dissecting animals. The great Roman physician Galen, who served as a doctor to gladiators, learned a vast amount about the human body by treating the horrific injuries he saw every day. His writings on anatomy and surgery became the standard medical textbooks in Europe for the next 1,500 years. The Romans had a system of organized medical care. The army had its own medical corps with dedicated field hospitals. The cities had public physicians. There was a clear professional class of doctors who were trained, skilled, and equipped with sophisticated instruments. This was not folk medicine. This was a systematic, evidence-based approach to surgery that was far ahead of its time. After the Roman Empire collapsed, much of this knowledge was lost in the West. Surgery became a less respected and more dangerous practice, often performed by barbers rather than physicians. The sophisticated tools were lost, and the anatomical knowledge faded. It took more than 1,000 years for surgical practice in Europe to climb back to the level of skill and sophistication that the Romans had achieved. How did Roman society support such an advanced level of surgical practice? What kind of training did these surgeons undergo? Given their lack of modern anesthesia and antibiotics, how did they manage to perform such invasive procedures with any degree of success? And how many lives were lost in the millennium after Rome fell due to the forgetting of simple surgical techniques that had once been common knowledge? Number 9. How could a chariot always point south? Imagine a machine that knows which way is south, not with a magnet, but with gears. This was the south-pointing chariot, a legendary invention from ancient China. According to historical texts, it was a two-wheeled chariot with a figure of a person mounted on top. No matter how the chariot turned, twisted, or changed direction, the figure's arm always pointed south. It was a mechanical compass. The first south-pointing chariot is said to have been invented by the legendary Yellow Emperor or his minister Fang Bo around 2600 BC. More reliable historical accounts place its invention during the Han Dynasty around the 1st or 2nd century AD. The great mechanical engineer Ma Jun is credited with building a fully functional one in the 3rd century AD. The problem is, no original chariot has ever been found. All we have are descriptions in ancient texts. For centuries, people debated whether it was real or just a myth. So how could it work? The descriptions do not mention magnets. The secret was not magnetism, but mechanics. It was an incredibly clever system of gears. The mechanism was a form of differential. A differential is a set of gears that allows an output to be the difference between two inputs. In a modern car, the differential allows the outer wheel to turn faster than the inner wheel during a turn, which is essential for smooth cornering. In the south-pointing chariot, the gears were connected to the two wheels of the chariot. When the chariot moved in a straight line, both wheels turned at the same rate, and the pointer did not move. But when the chariot turned, one wheel would travel a slightly greater distance than the other. This difference in rotation was fed into the gear system. The gears would then turn the pointer on top by the exact amount needed to counteract the turn of the chariot. So, if the chariot turned 30 degrees to the left, the gears would turn the pointer 30 degrees to the right, keeping it fixed on its original direction. This is a mind-bogglingly complex concept. It required a precise understanding of gear ratios and mechanics. To design and build such a device with the tools available in ancient China would have been an immense challenge. The gears had to be perfectly cut and meshed to avoid slipping, which would throw off the direction. Modern engineers have built replicas based on the ancient descriptions, and they work. It is a testament to the mechanical genius of ancient Chinese inventors. While the compass, which used magnetism, was also a Chinese invention, it was initially used for spiritual purposes like feng shui. The south-pointing chariot was a purely mechanical navigational device used for navigating vast, featureless plains or for ceremonial purposes to ensure the emperor was always properly oriented. This was a technology that was far more complex than any gear system known in Europe at the time. The concept of the differential gear did not appear in the West until the 16th century, and it was not perfected until the 19th. The Chinese had mastered it over 1,000 years earlier. Since no ancient examples survive, can we ever be sure exactly how they were built? Was the design passed down through secret texts known only to a few court engineers? And why did this incredible mechanical knowledge not lead to a broader mechanical revolution in China, similar to what happened in Europe much later? Number 8, how could a dragon tell you where an earthquake was? In the year 132 AD, in the court of the Han Dynasty in China, a scholar and inventor named Zhang Heng presented a remarkable device. It was a large bronze vessel about 6 feet in diameter. On the outside, it was decorated with 8 dragons, each one facing a different direction of the compass. In the mouth of each dragon was a small bronze ball. Below each dragon, sitting on the base of the vessel, was a bronze toad with its mouth open, looking up. This was not just a work of art, it was the world's first seismoscope. It was a machine designed to detect earthquakes from a distance. And according to historical records, it worked. One day, one of the dragons suddenly dropped its ball. The ball fell from the dragon's mouth into the mouth of the toad below, making a loud clang. The dragon was the one facing west. The court officials were confused. There had been no tremor felt in the capital, Luoyang. But a few days later, a messenger arrived from a region several hundred miles to the west. He reported that a major earthquake had just occurred there, at the exact time the machine had been triggered. The court was astonished. How did it work? The secret was on the inside. Zhang Heng's original device is lost, and his exact design remains a mystery. But historians and scientists believe the core of the machine was a pendulum system. Inside the bronze vessel, a heavy pendulum was suspended. When the seismic waves from a distant earthquake reached the instrument, the ground would shake. The vessel would move, but the heavy pendulum, due to its inertia, would remain relatively still. This relative motion between the pendulum and the vessel would cause the pendulum to swing and hit a system of levers inside. The lever corresponding to the direction of the tremor would then be pushed. This lever, in turn, would open the mouth of the correct dragon on the outside, releasing the bronze ball. It was a simple, elegant solution to a very complex problem. Zhang Heng's seismoscope was a revolutionary invention. It was the first time in history that anyone had created an instrument to detect a natural phenomenon that was happening hundreds of miles away. It represented a major shift in thinking. Earthquakes were not just the unpredictable wrath of the gods. They were a physical event that could be detected and, to some extent, understood. The technology was more than 1,700 years ahead of its time. The first modern seismographs that could detect and record earthquakes were not developed in Europe until the late 19th century. Zhang Heng had created a device that could do the most important part, detect the event and indicate its direction. nearly 2 millennia earlier. Without the original machine to study, can we ever be certain about the exact mechanism inside? How sensitive was it really? Was its success a one-time event, or did it regularly and accurately report distant earthquakes? And how could such a profoundly important scientific instrument, a window into the inner workings of the Earth, be built and then have its technology completely forgotten for centuries? Number 7. How did a crystal help Vikings navigate on cloudy days? The Vikings were masters of the sea. From the late 8th to the 11th centuries, they sailed from their Scandinavian homes to raid and trade across Europe and the North Atlantic. They reached Iceland, Greenland, and even North America nearly 500 years before Columbus. They did this in open longships, navigating vast, featureless oceans. They did not have magnetic compasses. So how did they find their way? The answer, according to Viking sagas and recent archaeological evidence, might lie in a mysterious object called a sunstone. The sagas are epic stories that mention these stones. They describe how, on a cloudy or foggy day when the sun was hidden, a Viking navigator could hold up a sunstone and it would reveal the sun's position. For a long time, historians thought this was just a legend. But in the 1960s, a Danish archaeologist named Thorkild Ramsku proposed a scientific explanation. He suggested that the sunstone was a piece of a specific type of crystal, probably cordierite or Iceland spar. These crystals have a special property called polarization. Sunlight, as it passes through the Earth's atmosphere, becomes polarized. This means the light waves tend to vibrate in a particular direction. The pattern of polarization in the sky forms a set of concentric rings centered on the sun's position. This pattern exists even on cloudy days. Humans cannot see this polarized light, but a crystal like Iceland spar can. When you look through a piece of Iceland spar and rotate it, the polarized light from the sky will appear brighter or dimmer depending on the crystal's orientation. By rotating the crystal until you find the point where the light passing through it is brightest or darkest, you can determine the orientation of the polarized rings in the sky. From that, you can pinpoint the exact location of the hidden sun. Once you know where the sun is, you can use a sundial to determine your direction. For decades, this was just a clever theory, but then evidence started to appear. In 2013, a cloudy whitish crystal of Iceland spar was found in the wreck of a 16th century English ship that sank off the Channel Islands. The ship had cannons and navigational dividers, suggesting it was found with other navigational tools. While not a Viking ship, it proved that such crystals were kept on board ships for navigation long after the magnetic compass was common. This suggests the technique was real and passed down through generations of sailors. The experiments, conducted by researchers like Guy Ropars at the University of Rennes in France, have shown that Iceland spar can be used to locate the sun's position with an accuracy of within 1 degree even when the sun is below the horizon at twilight. It is a highly effective navigational tool. The Vikings were using a deep principle of physics, the polarization of light, to navigate. They did not know the science behind it, but through observation and experimentation, they found a material that allowed them to see something that is invisible to the naked eye. It was a piece of high technology born from a clever use of a natural material. How did the Vikings first discover this remarkable property of a specific crystal? Was it a closely guarded secret among navigators? And are there other ancient legends of magical objects that are actually descriptions of forgotten scientific tools based on principles we have only recently understood? Number 6. What fire burned on water? In the 7th century AD, the Byzantine Empire was in trouble. It was besieged by Arab fleets. Its capital, Constantinople, was under threat. The empire needed a superweapon, and it got one. It was a terrifying, mysterious substance known as Greek fire. Greek fire was an incendiary weapon. It was a liquid that could be sprayed from siphons mounted on the front of Byzantine ships. When it hit an enemy ship, it would burst into flames. But this was no ordinary fire. It could not be put out with water. In fact, pouring water on it often made it burn more intensely. It would stick to ships and to people, burning everything it touched. It was the napalm of its day. The invention of Greek fire is credited to a man named Kallinikos, a Greek-speaking refugee from Syria, around the year 672. He brought the secret formula to the Byzantine emperor. It was an immediate success. The Byzantine navy used it to destroy Arab fleets and save Constantinople on at least 2 occasions. It gave them a technological edge that helped the empire survive for centuries. The formula for Greek fire was one of the most closely guarded state secrets in history. It was known only to the emperor and a select few families of technicians who manufactured it. They knew that if the secret got out, they would lose their advantage, and they were successful. The exact recipe for Greek fire was never discovered by their enemies. In fact, it was so well kept that it was eventually lost to history. We still do not know exactly what it was made of. Modern historians and chemists have tried to reconstruct the formula based on historical descriptions. The general consensus is that the main ingredient was probably petroleum or naphtha, a light form of petroleum. This would have been readily available in the Middle East. This base would have been mixed with other substances. Some suggested ingredients include sulfur, which would add to the heat and smell, and quicklime. When quicklime is mixed with water, it heats up rapidly. This might explain why water seemed to make the fire worse. Other possibilities include pine resin, which would make the mixture sticky, and saltpeter, an oxidizing agent that would help it burn even without air, perhaps allowing it to burn even on the surface of the water. The delivery system was just as important as the chemical mixture. The Byzantines used bronze pumps and siphons to project a stream of the burning liquid at their enemies. It would have been a terrifying sight, a jet of flame shooting across the water, setting ships ablaze. And Greek fire is a perfect example of a technology that was far ahead of its time. It was a complex chemical weapon that required a sophisticated understanding of chemistry and engineering to produce and deploy. Nothing like it would be seen again until the development of modern chemical weapons in the 20th century. What was the exact formula that was so carefully guarded for centuries? How did they manage to handle and deploy such a volatile and dangerous substance without constantly having accidents? And what does the story of Greek fire tell us about the power of a single, secret technology to change the course of history? Number 5. Why did this paint last 2,000 years? In the Fayum region of Egypt, during the Roman period from the 1st to the 3rd centuries AD, a unique form of art flourished. People would have incredibly realistic portraits of themselves painted on wooden boards. When they died, this portrait would be placed over the face of their mummified body. Hundreds of these Fayum mummy portraits have survived. What is stunning about them is not just their haunting beauty, but their condition. The colors are still as bright and vibrant as the day they were painted, nearly 2,000 years ago. These are not frescoes or oil paintings. They were painted using a technique called encaustic painting. The artists used pigments mixed with hot beeswax. They would then apply the molten colored wax to the wooden panel. They could use brushes or other metal tools to shape and model the wax, creating subtle textures and a sense of three-dimensional depth that is truly lifelike. Encaustic painting is an incredibly difficult technique. The artist has to work quickly while the wax is hot, but the results are worth it. The beeswax is a superb binder for the pigments. Talents in the direction is just waterproof and resistant to decay. It creates a rich, luminous quality. The wax seals the pigments from the air and moisture, which is why the colors have not faded over 2 millennia. The Roman writer Pliny the Elder described the technique in his Natural History. He wrote about its use on ships where a waterproof coating was essential and in art. The Fayum portraits are the best surviving examples of this lost art form. The artists who made them were masters. They captured the individual personalities of their subjects with a directness and humanity that feels incredibly modern. You feel like you could meet these people on the street. After the Roman era, the complex and difficult technique of encaustic painting largely fell out of use. It was replaced by simpler methods like tempera and later oil painting. The secret of how to work with the hot wax was mostly forgotten. It was not until the 20th century that artists like the American painter Jasper Johns began to revive the technique. The Fayum portraits show a level of artistic technology that was far ahead of its time. The painters had a sophisticated knowledge of their materials. They knew how to select pigments and mix them with beeswax to create a paint that was not only beautiful, but also incredibly durable. This was materials science in the service of art. What was the exact recipe for their wax medium? Did they add other substances like resin or oil to change its consistency? How did they manage to achieve such fine detail and subtle blending with such a fast drying and difficult medium? And what other advanced artistic techniques have we lost? Their secrets buried with the civilizations that created them. Number 4, how did China's first emperor chrome plate his weapons? In 1974, farmers digging a well in Xi'an, China, made one of the greatest archaeological discoveries of all time. They found the terracotta army. This was a vast underground collection of thousands of life-size clay soldiers, horses, and chariots built to guard the tomb of Qin Shi Huang, the first emperor of China who died in 210 BC. The army is famous for its scale and the individual detail of each soldier. But hidden among the clay figures was a technological marvel that baffled scientists. Many of the bronze weapons found with the soldier swords, crossbow triggers, and spear tips were in astonishingly good condition. After being buried for over 2,200 years, they were still sharp and shiny. When archaeologists first analyzed them, they found a thin layer of chromium oxide on the surface of the bronze. Chromium plating is a modern technique. It was discovered by German scientists in the 1920s. It involves applying a thin layer of the metal chromium to another object. This layer is extremely hard and protects the object from corrosion. It is what gives bathroom fixtures and car bumpers their shiny, rust-proof finish. Finding what looked like chromium plating on 2,200-year-old weapons was incredible. It suggested that the Qin dynasty weapon makers had developed a technology that was 2 millennia ahead of its time. For decades, this was presented as a great mystery of ancient China. How did they invent chrome plating? The theory was that the Qin artisans used a chemical process, perhaps dipping the bronze weapons in a solution containing chromium salts, to create the protective layer. However, recent research has changed the story. A detailed study published in 2019, led by researcher Marcos Martinon Torres, challenged the idea of intentional chrome plating. The scientists analyzed hundreds of weapons and soil samples from the site. They found that the chromium on the weapons was not evenly distributed, as you would expect from plating. Instead, it was concentrated in patches. More importantly, they found that the soil around the terracotta army was naturally rich in chromium. The best preserved weapons they discovered were not the ones with the most chromium. The key to their preservation was the bronze alloy itself, a high-tin bronze that is very resistant to corrosion, and the moderately alkaline, fine-grained soil of the pit, which sealed them from air and water. So, the chromium was likely not an ancient super technology. It was probably a contaminant from a lacquer that was used to treat the terracotta figures and weapon handles, which then contaminated the bronze. The chromium did not protect the weapons. The weapons were so well made, and the burial conditions so good that they protected themselves. While this solves one mystery, it highlights another. The real head of its time technology was not chrome plating, but the incredible skill of the Qin metallurgists. They were able to mass-produce huge quantities of high-quality bronze weapons with a consistency and durability that were unmatched. They had created a sophisticated assembly line-like production system that was a marvel of industrial organization. So, the question changes. How did the Qin dynasty develop the logistical and metallurgical expertise to equip an entire phantom army with such perfectly crafted and durable weapons? What quality control methods did they use? And does this story teach us that sometimes the real ancient marvel is not a mysterious lost secret, but a level of craftsmanship and organization that is simply hard for us to comprehend? Number 3, could you see through ancient glass? We think of glass windows as a relatively modern convenience. For most of history, windows were just open holes, covered with shutters, animal hides, or oiled paper. But what if some ancient people had something much closer to the real thing? The story of ancient glass is more complex than we think, and it includes one very mysterious object. In 1853, the archaeologist Austin Henry Layard was excavating the palace of an Assyrian king in what is now Iraq. The palace dated to the 8th century BC. In one room, he found a small oval-shaped piece of rock crystal. It had been ground and polished. It was, for all intents and purposes, a lens. This object is now known as the Nimrud lens. The Nimrud lens is about 1.5 inches across and has a focal length of about 4.5 inches. It can magnify things by about 3 times. It is not a perfect lens. It has some flaws, but it works. The question is, what was it for? There are several theories. The man who first examined it, a scientist named David Brewster, suggested it was part of a telescope. This is highly unlikely, as there is no other evidence that the Assyrians had telescopes. Another theory is that it was used as a magnifying glass, perhaps by a craftsman doing fine, detailed work like carving cylinder seals. This is plausible. A third theory is that it was used as a fire starter to focus the rays of the sun to create heat. This is also possible. Some have dismissed it entirely, saying it was just a piece of decorative inlay that happens to be shaped like a lens by coincidence. But the grinding and polishing seem too deliberate for it to be an accident. The Romans, who came centuries later, certainly knew about the magnifying properties of glass. The writer Seneca noted that letters seen through a glass globe filled with water appeared larger. Pliny the Elder wrote about an emperor who used an emerald to watch gladiator fights, possibly as a way to correct his poor vision. The Romans also developed the technology to make the first crude forms of window glass. It was thick, full of bubbles, and not very transparent, but it was a start. It let light in while keeping the weather out. The existence of the Nimrud lens, however, pushes the history of optics back much further. It suggests that as early as the 8th century BC, someone understood how to shape a piece of crystal to bend light in a useful way. This is the fundamental principle of all lenses, from eyeglasses to telescopes to microscopes. Was the Nimrud lens a one-of-a-kind freak, or was it an example of a more common technology whose other examples have been lost? Did ancient scholars or craftsmen use magnifying glasses to aid their work? Could a civilization have the basic building block of optics to the lens and not develop it further into more complex instruments? And what secrets might we be able to read in ancient texts if we only knew they were written by people who could see the fine print? Number 2, how did they build a concrete that lasts forever? We build things to last. But our modern concrete, the most common building material on Earth, often does not. Bridges, dams, and buildings made with modern Portland cement can begin to crack and crumble in as little as 50 years, especially in harsh environments like the sea. The ancient Romans, however, built concrete structures that have lasted for 2,000 years, and in some cases they are getting stronger over time. Roman harbors like the one at Caesarea in Israel were built with massive concrete breakwaters. These have been battered by waves for 2 millennia and are still intact. The Pantheon in Rome has the largest unreinforced concrete dome in the world. It was completed in 128 AD and is still standing, perfectly preserved. How did the Romans make a concrete that was so much better than ours? The secret, which modern scientists have only recently unraveled, lies in their recipe. The Roman engineer Vitruvius wrote about it in the 1st century BC. The key ingredients were volcanic ash, lime, and seawater. They would mix the lime and volcanic ash to make a mortar. Then they would pack this mortar, along with chunks of rock, the aggregate, into wooden forms. When this mixture came into contact with seawater, a powerful chemical reaction started. A team of researchers led by Marie Jackson at the University of Utah has studied Roman sea concrete in detail. Using advanced X-ray techniques, they found that the seawater dissolves components of the volcanic ash. This allows new, rare, and incredibly strong minerals to grow in their place. One of these minerals is called aluminum tubermarite. These interlocking crystals act like a natural reinforcement, filling in any microscopic cracks that form. This means that Roman concrete heals itself. Over time, as more seawater seeps into the structure, more of these strengthening crystals grow. The concrete actually becomes stronger with age. Modern Portland cement, by contrast, is a recipe for decay. When seawater gets into it, it dissolves the binding paste and weakens the structure. The Roman recipe is the exact opposite. This was a revolutionary technology. It allowed the Romans to build massive, durable structures quickly and cheaply, both on land and in the challenging environment of the open sea. It was the backbone of their architectural revolution, but after the fall of the Roman Empire, this recipe was lost. The specific knowledge of which volcanic ashes to use, they favored one from a region near Naples called pozzolana, and how to mix them was forgotten. People went back to building with stone and brick, which was much more laborious. The Romans had created a green technology. It used less energy to produce than modern cement because the lime was baked at a lower temperature. And it actively incorporated elements from its environment to make itself stronger. It was a perfect example of working with nature, not against it. Why did we lose this incredible recipe for over 1,500 years? Are there other ancient recipes for materials that are superior to our own, waiting to be rediscovered in old texts? And as we face the challenge of building a more sustainable world, what else can we learn from the engineers who built a city that was meant to be eternal? Number 1. What else did we lose? Each of these inventions tells a similar story. A story of a brilliant idea, a flash of genius that appeared long before its time. And then the knowledge was lost, sometimes for a few centuries, sometimes for more than a millennium. It is a pattern in human history. We discover something amazing, and then we forget it. The Antikythera mechanism, the Roman concrete, the Damascus steel, these are not just historical curiosities. They are reminders of our own fragility. They show that knowledge is not a straight upward line. It is a winding path, with many dead ends and forgotten trails. The idea that we are always progressing, that we are always smarter and more capable than the people who came before us, is a dangerous myth. These lost inventions force us to ask some fundamental questions. Why does knowledge get lost? Sometimes it is because of a societal collapse, like the fall of Rome, where libraries are burned and skilled craftsmen are killed or dispersed. Sometimes a crucial raw material runs out, like the Wootz steel for Damascus blades. Sometimes a secret is so well guarded that it dies with the people who kept it, like the recipe for Greek fire. And sometimes an idea is just too far ahead of its time, and the society is not ready to understand or use it, like Hero's steam engine. This leads to the final and most important question. What else is out there? What other lost inventions are still buried under the ground, or at the bottom of the sea, or hidden in the pages of a language we cannot fully understand? Are there other machines as complex as the Antikythera mechanism, other materials as advanced as the Lycurgus cup, other medical procedures as daring as trepanation? The past is not a dead, settled place. It is an active mystery. Every new archaeological find has the potential to rewrite our history books and challenge our assumptions. We think we are at the peak of human achievement, but perhaps we are just rediscovering things that our ancestors already knew. Perhaps we are just the heirs of a forgotten and far more brilliant world. What texts that we dismiss as myths are actually distorted descriptions of real technologies. How many magical items from folklore were just advanced science that people could no longer explain? And what is the most important invention that we have lost? The one that we do not even know we are missing?